Okay, hi everyone, and welcome to this talk. So I'm going to tell you a little bit about my joint work with Ross on graph streaming lower bounds. And let's go over the history pretty quickly. So the streaming model was introduced by Alan, Matthias, and Szegedi as a model of computation for processing very large amount of data on the fly with limited memory. So a good example is that think of a switch in a network that has to process all these incoming packets, and the memory of the switch has to be exponentially smaller than the input size. And now, based on this view, there are tons and tons of streaming algorithms for problems for primarily for estimation, statistical estimation problems, number of distinct elements, etc. But what about graph problems? This question has been asked many, many years ago. And the understanding is that this restriction seems to be really restrictive when it comes to graph problems. If you think about it, if you want a solution for, let's say, the minimum spanning tree problem, there's no way you can output a spanning tree of your graph with exponentially smaller memory than the input size. At the same time, it's also understandably that in many cases, these are unnecessarily too restrictive. Let me show you an example of streaming algorithms. Say you have these social networks and you want to process it on your laptop. And streaming algorithms are super useful here because you can just read this network in one pass, go over its, let's say, the hard drive or wherever this graph is stored, just read it in one pass in a sequential way, which makes it very efficient in terms of I/O. Then you have a limited memory on your computer to process it. And that's how lots of graph streaming algorithms are being used. And if you think about it now, actually, the memory of your algorithm is not exponentially smaller than the size of the input. In fact, in many cases, if you can just make a quadratic improvement inside the memory, then it will fit your main memory and you can solve the problem. Another important aspect here is that, in fact, in this example, for instance, it will not be too awful if you couldn't process your entire graph in one pass and you decided to make one more pass over the input. This is very different from a network that the data is just completely lost after it passes through the router or the switch. So based on this observation, Feigenbaum et al. Introduced this graph streaming model, basically by saying that let's allow the algorithms more memory, often proportional to the number of vertices, called the semi-streaming algorithm, and also more passes if necessary, maybe a constant or sometimes even a logarithmic passes. Again, based on this, there are tons and tons of graph streaming algorithms now, and there are also lots of application of these algorithms in particular because they are very, very I/O efficient. Good. So now that I told you about the story, let me tell you about the formal definition of the model. Here we assume that we know the vertices beforehand. These are just numbers from 1 to n. And then the edges are written inside the stream. And then the streaming algorithm has a limited memory and can read these edges sequentially. So this is the first pass of the algorithm. It's going to read all of them. At the end of the pass, it may output the solution, or if in case it's a multi-pass algorithm, it may even read it one more time or a couple of more times in the same order and then output the solution. Now here, a graph with n vertices can have up to n square edges. And so if the memory of the algorithm is order n square, then of course it can store the entire input and solve the problem. But what if the memory is much, much smaller than n square? Then something non-trivial should happen by the algorithm. Similarly, as I said before, we really want the algorithm to make just one pass. But if we know that one pass does not work, it will not be a deal breaker in many cases to allow the algorithm to make its second pass or even a small constant. And in fact, in the literature, there are even algorithms that make, let's say, log n passes over the input. And I want to emphasize something here is that in a streaming model, unlike some other similar model, here we are really trying to optimize the number of passes down to the last constant. So you may see lots of streaming algorithms that say they claim to get a 3-pass algorithm, not an order 1-pass algorithm. You'll try to optimize to, let's say, get 3 instead of 5. Okay, so now that I tell you about the history of this model and the definitions, let me tell you about the state of the art. And there is this big asterisk here. I'm going to do a bit of lying and do lots of oversimplification to tell you the story really with respect to our paper. So with that caveat, then I guess it's fair to say that for single pass algorithm, we have a relatively good understanding of what is happening. And if I want to put it in a few words, I should say that exact problems are hard. They require omega in a square space. And what do I mean by that? Finding a perfect matching, finding a maximal independent set, solving shortest path exactly. All of these problems provably require omega in a square space. But some approximations often to most of these problems are also possible. We can usually get very good good approximations in O tilde n space. Let's say 2 approximation to matching, log n approximation to shortest path, or 1 plus epsilon approximation to mean count. And again, let me just also say that this is a very wide brush to paint everything with it. And it's not really fair. Like there are lots of, there's still a lot of research. We don't have a good understanding of what is the right approximation factor for these problems. And that's a very active area of research. But for our purpose, let's just categorize into these things that exact problems are hard and some approximations are doable. Good. But then what happens if I allow a couple of more passes to the algorithm? And right away, things start to get murkier. For instance, well, we know that we can save in the space dramatically, even with a couple of more passes. As a good example is testing whether your graph is triangle-free or it has lots of triangles. And here we know that by allowing just 3 passes, you can improve your space by quadratic factor, basically. Or we also know that in the same space, you can do much better in terms of approximation. For instance, for the dominating set problems, in n to the 3 half space, best single pass algorithm can effectively only get a square root n, while in 2 passes, we can get even a log n approximation to the problem within the same space. Good. But in fact, the most glaring example is even for this problem of finding a global min cut of a graph in an undirected, unweighted graph, find its global min cut exactly. Here it turns out that we knew for quite some time that in 1 pass you need omega in a square space, but some recent work showed that in fact, even in just 2 passes, we can solve this problem very efficiently in O tilde n space, or even order n log n bits. So this seems like already from 2 passes, the powers and limitations of graph streaming algorithms are not that clear anymore. We saw an example of, for instance, an exact problem which, like min cut, which would effectively, we usually think of it as a hard problem, but we see that we can solve it exactly in 2 passes. So then what are some other problems? Can we solve maximum flow, maximum matching, reachability, shortest path, etc.? And the answer to this question turns out to be a bit hard because of 2 reasons. One is that it seems that we barely scratched the surface of the power of multi-pass streaming algorithms. They seem to be really, really powerful. Okay? And we still don't have a good understanding of them. And another reason it seems that we also don't have good tools and techniques for proving strong lower bounds for multi-pass algorithms. Okay? And this is what we are going to focus on this paper. Okay? We want to start proving a stronger lower bounds for multi-pass algorithms. And let's start with a very modest goal in this paper, just proving lower bounds for 2-pass algorithms. This is what is happening. Now let me tell you about our result. Basically, we studied several fundamental graph problems. Let's say ST reachability in a directed graph. Can S reach T or not? Or shortest path in an undirected graph. What is the length of shortest path from S to T? Or matching problem. Given a bipartite graph, does it have a perfect matching or not? And for all these problems, we know for quite some time that in 1 pass, we need omega in a square space. But already from 2 passes, the lower bounds become much weaker, and they are almost just a bit more than linear. Okay, so n to the 7/6 space. But I should say that this second type of lower bounds, they continue to go up to the log n passes, or log n divided by log n, and even there, they are still super linear. Okay. although the trade-off changes from 7/6. Good. Now, what do we prove in this paper, on the other hand? We show that for all these problems that I mentioned, even in two passes, we need almost a quadratic space. So there is no algorithm that uses n to the 2 minus the small o of 1 space and solve the problem in two passes. And what this means is that effectively there is no non-trivial solution to these problems, because basically we can just store the graph in n square space in one pass and solve the problem. So it shows that these problems at least are really hard, even in two passes. And a bit more formally, we prove that any two-pass algorithm, deterministic or randomized for any of these problems that I mentioned, a bunch of other ones that follow from reductions, require roughly n squared divided by 2 to the square root log n space. Good. And I will tell you a bit more about these numbers, but let me just say that this number basically comes out of using the best known construction of this so-called Ruzsa-Szemeredi graphs, which have been extremely powerful in recent years in proving graph streaming lower bounds, starting with this very nice work of Goel, Kapralov, and Kano. And our work shows another perhaps surprising application of these graphs. Okay. And just to say one word is that the way we prove our lower bound is to prove communication complexity lower bounds in a slightly non-standard two-party model, but I won't get to details of that. And then once we have this lower bound for the reachability problem, all the streaming result for reachability and other problems follow with just some simple reductions. So now let me spend the rest of the talk tell you a little bit about how we prove this result. Basically, we'll start with looking at some simple single pass problem, which is just the following. Let's say you have your graph G, you have a single vertex S. There's this set U with the promise that S can just reach one vertex chosen uniformly at random among you. So the only vertex in U that S reaches is S star, and S star is chosen uniformly at random from you. Good. And then the goal is to find this S star. And let's say that we prove such a problem is hard. Okay, it requires omega n square space, for instance. Then what we can do with this problem? Well, we can take that graph and make two different copies of the graph. And for the other copy, let's just reverse the order of edges. So now this way there will be a unique vertex T star that can reach T among that set. So we put these two copies of the graph. Then we pick a random bipartite graph and connect these two target sets to each other by edges from left to right. If you look at this graph, it's easy to see that the only way for S to reach T in this graph, if there exists an edge between S star and T star. If the edge exists, we can just follow. This is the path that's all that make S reachable, that help S reach T. If that edge doesn't exist, by the promise that S star is the only vertex reachable on left and T star is the only vertex on right that can reach T, it's easy to see that there is no way for S to reach T. So now let me show you why solving such a problem, ST reachability over these graphs, is hard in the streaming. But let's say that the edges of the graph, first the edges of the bipartite graph appear, then the edges on the left, then the edges on the right. So then the streaming algorithm can just basically make one pass over these edges and then another one, or one total pass over this long sequence of edges. Let's go over what happens with the algorithm. Well, the first time algorithm sees E1, it doesn't know which edge is important. There are tons of edges there, so it's going to forget about the important one. Then it sees E2. By the guarantee that we have from the single pass algorithm, in this pass, it will not be able to figure out what is S star. The same way happens for E3. So by the end of the first pass, the algorithm has not figured out what is S star, what is T star. Good. It again sees edge E1. It doesn't know, because still S star and T star are known to the algorithm. So it doesn't know, it has to pick it. Again, there are tons of edges and it's going to forget about this edge. And then after this, it doesn't matter. Even if you figure out what are S star and T star, you don't know whether that edge existed or not, okay? And so you won't be able to solve the problem. So do you see a problem with this approach, however, that I told you? And the thing is that I oversimplified the things. Really, if you want to design an algorithm, consider there is no reason that you should really try to find S star or T star. In fact, if you're able to just limit what are the choices for S star and T star in the first pass, you're going to be done. Because in the first pass, you're going to say that, look, S star is in this smaller set, T star is in this set. And so in the second pass, you're just going to store all the edges between these two. Because now these sets have shrunk enough, you will be able to store them in much less than a square space. Okay? Then you can solve it in 2 passes. So this will break the lower bound if that happens. So what this means for us is that the single pass lower bound that I talked about has to be very strong. It should effectively say a sentence like this. After the first pass, the algorithm has no idea what is S star and T star. It should not reveal any information about them. And that's what we are going to prove. And to prove that, we need 2 ingredients. One is to how to use this Ruzsa-Szemeredi graph. And the other one is this notion of epsilon solving a set intersection problem that I will tell you about. And once we have these things, then we can follow some sort of a standard argument based on pointer chasing in communication complexity and solve the problem. So now in the rest of the talk, let me tell you a little bit more about these ingredients, starting with RS graphs. In quick definition, in a graph, I'll say that a matching of a graph is induced if there are no other edges between the vertices of the match. So this is an induced match. Now I say that a graph is RT-RS graph if its edges can be partitioned into T induced matching, each of size R. So this is a 3x4 RS graph, one induced matching, another. And we are interested in finding RS graph that have both very large R and T. And if you think about it, this seems like a counterintuitive statement because these are locally sparse graphs. There are tons of matchings with no edges between them. But at the same time, they have to be globally dense. But it turns out that interestingly, such graph exists. And one nice construction is already given by Ruzsa-Szemeredi that gives R slightly sublinear in N and T linear in N. And that's how we get the parameters. And that's what and this is the graph we are going to work. So how do we create our construction? Well, this is for the one pass problem. S has to find S star. So we put a bipartite RS graph in the middle, and then we direct the edges from left to right. So this one of the induced matching, it is directed. It has a bunch of other induced matches. This is the first part of the stream. This is what Alice gets. Then Bob is going to get the edges incident on S and this set of target elements. And these edges are going to exactly one of these induced matchings chosen uniformly at random. So S is connected to everyone here. These vertices will be connected to the right-hand side. Good. How are these connections are made? Well, the edges that Alice and Bob have, remember Alice has these edges and Bob has these edges, and this part is always complete. Now these edges form an instance of set intersection, meaning that Alice has a bunch of edges here A, Bob has a bunch of edges B here, with the promise that their intersection is unique. There is just one edge that is uniquely intersected by both elements. Basically, the edges look like something like this. And if you now see, there is just, from S, there is just one path, now that we use the inducedness of this matching, that will take this edge and will bring it to this vertex here. And this is going to be our S star vertex. The unique vertex in this set that we talked about is basically just the answer to the set intersection problem. And with that setting, we can reduce the problem to the following. Alice has a bunch of sets that each of them are roughly size n. Like she has roughly n sets, each of size n, almost again, okay, a bit less than that. And she sends a single message to Bob, and Bob has just one set and one index of Alice's set, and has to solve the set intersection problem for that particular index. So find the intersecting element. And what do I mean by find now? Remember that we don't need to find S star. So now let's talk about that. And that brings us to the second ingredient. Well, let's go back and look at the original set intersection. Alice has this set, Bob has this set, and they intersect only on this element. And so if the protocol works correctly, after it's finished, Alice can just look at her input and say that, oh, look, previously the target element could have been each of these elements. Now I know it's exactly this. This is the notion of finding the set intersection. And very nice classical result already proved that this problem requires a lot of communication between the players. On the other hand, what we need is this thing we call internal epsilon solving. It's basically, Alice does not need to really figure out what is the intersection. She should just be able to change the distribution of each element. Say that, look, the first element, this is less likely to be the target. This is less likely, more likely, etc. Okay? And the same way for Bob. A bit more formally, this means that after we do the communication, is Alice look at her input and look at the distribution of target element condition on her input, this distribution should become very different after the communication has happened. Let's say by epsilon in total variation distance. Good. And I will not tell you exactly how, but if you think about it, this problem is much, much simpler algorithmically than finding the intersection. Good. And still, we are able to prove that, in fact, even this problem requires a lot of communication. Epsilon solving requires omega epsilon squared times the minimum size of the sets. So for constant epsilon, this is still as hard as really just finding the intersection itself asymptotically. Good. So we'll prove this in the paper. Now, how are we going to use this? Well, again, remember that Alice had tons of sets. She didn't know which one is the special one. So, and she has to send a message, and then after that, her message should be able to solve the set intersection according to this notion for the particular set that Bob has. So there are n independent instances of the problem. We said that solving one of them requires r bits of communication, roughly. And so because there are t independent instances, we want to say that this becomes t times harder, which if you do the math, this thing becomes roughly n square space. This is exactly what one can prove using now these standard arguments based on information complexity. So after we prove this basically allows us to say that after the first pass, with less than n square communication, distribution of S star and T star are going to remain almost basically the same as if they were uniform to begin. And now after we have this, and then using this notion of internal, etc., we are also able to show that after the second pass, if after the first pass S star and T star are uniform, after the second pass, whether that particular edge that we care about exists or not, that distribution has only changed again very slightly from uniform distribution. And I will not go over this part at all. But now that we prove this, then we can say that, look, the algorithm answer is exactly only a function of whether this edge exists or not, but its distribution is almost uniform. So the algorithm cannot solve the problem with probability better than half. That's how we get the law. Now let me quickly conclude. Well, we prove near-quadratic space lower bound for a bunch of graph streaming algorithms in two passes, such as problems such as reachability, shortest path, and bipartite match. The tool we used were RSgraph, this set intersection, and some pointer chasing arguments. Now from now on, there are a bunch of nice open problems. The immediate question is can we go beyond the two passes? And that seems a very promising direction to look. But after that, it's really, can we go even beyond log n passes? As I told you, it seems that log n is still at the threshold of being a reasonably number of passes. Are these problems solvable even in log n passes? And here, these are a bit hard question how to go above even log n passes. And we don't know many lower bounds there. In fact, one of the few lower bounds we know are some for very hard problems such as capacitated max flow or lexicographically first MIs that we can prove even polynomial number of passes on it. So But I think the most important question here to understand is that really what is the true power of like two-pass algorithms or three-pass algorithms, and uh, can we again characterize what, even in a very roughly, what are the type of problems we expect that are solvable and what problems are hard? What makes min-cut a problem that we can solve in two passes but not shortest path? I think that's a very nice question if one can even pose it correctly and then answer. And that's all I wanted to say. Thank you.